Hello, this is our second lecture under week 3, where we're still discussing open channel flow concepts. So we did an introduction to open channel flow during our last lecture. We showed that for an incompressible fluid, where a wave on top of that fluid is much more shallow or much smaller than the wave in the channel, we can solve with wave equations to show what kind of flow regime our channel is in based on its velocity. So we can show that it's either in supercritical flow, which is shallow and fast. We showed that it could be in subcritical flow, which is deep and slow, or it could flow in critical depth. And then we showed on our energy curve that critical depth falls in the middle of that energy curve at the minimum energy, and that there's two solutions for a depth in a channel. There's two solutions for any given energy. And then we showed that when we go between these two solutions, we get gradually varied flow as we go down from subcritical to critical. And then as we go into supercritical, we can get back into uniform flow on either super or sub. And then we showed that when we go from supercritical back to subcritical, we exchange kinetic energy back into potential energy, and we have what's called a hydraulic jump. So we went over uniform flow, gradually varied flow, and rapidly varied flow. And today we're going to expand on uniform flow. Today we're going to derive, under uniform flow assumptions, the most commonly used equations to size a channel, to design a channel, and to estimate the flow rate in a channel. And that equation we're eventually going to get to is called the Manning's open channel equation. And to get that, we make some assumptions. We make uniform flow assumptions for a fluid that is highly turbulent. Remember that all of us, we are always in a highly turbulent flow condition in open channel hydraulics. So we don't use the Reynolds number, we use the Froude number. Now, what are these uniform flow assumptions? What are our uniform flow assumptions? Uniform flow assumptions. Right? We assume the depth does not change with distance. So the change in depth over the distance is equal to 0. We assume that it doesn't change as we go down this channel. That's uniform flow. And then we also assume that the flow depth is perpendicular to the bed slope, the channel bed slope. So we assume that our water surface and our bed surface are perpendicular. So how does that help us derive some of these commonly used equations? So let's consider a channel that has a channel bed slope, has a ground surface, and inside that channel is some water. That water has some depth y1 and some depth y2. But we know that y2 equals y1 under our assumptions. There is a hydrostatic force on that water. We're going to call that force F1. And at the other end of this column that we're using, this water column, there's also an equal and opposite hydrostatic force that we're going to call F2. Now this column has some length to it, L. Right? There's some length, L, of this column of water that is in a channel that has y1 equals y2, and those flow depths are perpendicular to our channel bed. So this length of water has some weight to it. It has some weight W. And the vector of that weight, the force of that weight, is angled at some angle theta. And that theta is the angle of our bed slope. So what we're trying to solve for under uniform flow is the force equal and opposite of the forces of this water, which we call shear stress. And this force that is opposite is shear stress, T sub W, times P times L. Well, what is P? If we take a section across this channel, I'll call it little a. Our section little a is a cross section of our channel geometry. And in that channel, there is water. And the perimeter of that water that's wet, that is P. That is the wetted perimeter. So how can we solve this problem? Right? We're assuming uniform flow, an incompressible fluid that is somewhere on length L with a wetted perimeter P. So we want to solve the forces. So if we sum our forces, and we set them equal to 0, we can begin to solve the statics of this water column. Well, we know that the force 1 equals force 2. And we know that y1 equals y2. And therefore, force 1 equals force 2. So those are gone. That means we can simplify this equation to find our shear stress is equal to the weight times the sine theta, the angle of the bed slope, divided by the wetted perimeter times the length of this segment, this hypothetical segment. Well, we can simplify sine theta, right? If we assume, let's assume that the slope is not steep. That slope, the bed slope, is not steep. That puts sine theta to approximately equal to its tangent, which means that's approximately equal to the bed slope. So now our equation has been simplified. The tau is equal to the weight times the bed slope divided by the wetted perimeter times its length. Well, what is the weight of the water? The weight of the water is equal to the unit weight of water times the area of that water times its length. So now our tau theta is equal to the unit weight of water, the area, the cross-sectional area of flow, the length of our channel segment, divided by the wetted perimeter times the length of our channel segment. So our lengths now have canceled each other out. So now let's make one more assumption. Let's assume let's assume a turbulent flow boundary on the channel bed. Let's assume a turbulent flow boundary on the channel bed. And if we make that assumption, we get something called dynamic pressure, where the dynamic pressure is also known as wall stress. And that wall stress is equal to the density of water, since it's incompressible, times v squared over 2 times k, where k is some sort of roughness, the roughness of that bed. So we have two equations for the shear stress. We assume the static solution for our water column, and then we assume there's a highly turbulent flow and some sort of roughness on this channel bed. And that gives us the dynamic pressure equation, which is v squared over 2, the density of water, and some sort of roughness. So now we can set these equal to each other. And I forgot the square root of the slope up here. So let's define one more term here. Let's take A over P out of this term. So we can say that the hydraulic radius is equal to A over P, and we're going to call that the hydraulic radius. And it's in units of feet. Feet squared over feet is feet, or length squared over length is length. So now we have the dynamic wall stress is equal to the unit weight of water, the hydraulic radius, and the slope of the channel bed. So if we begin to solve for velocity, we can start solving for velocity. Now, what's the unit weight of water? The unit weight of water for incompressible fluid is density times its gravity. And I forgot the 2 up here. So 2 times this. So if we take, so that gets rid of this density, since that's density of water times gravity. So this is gone. This turns into gravity. And our roughness K is still here. So let's call roughness K constant, and gravity is a constant. We now have separated our constants. 2g over k, roughness is equal times the hydraulic radius and the slope of the channel bed is equal to the square of the velocity, or in other terms, let's just say that 2g over k is some constant c, or in other terms, the velocity is equal to, let's call it the square root of c times the square root of the hydraulic radius times the bed of the slope. Okay, so we just made some uniform flow assumptions. That the depth in the channel does not change over distance, that depth is perpendicular to the bed of the slope, that the bed of the slope of the channel is relatively mild, meaning that it's less than 1, that the fluid is incompressible, so that the density and the gravity do not change. The viscosity isn't changing with our density, with our pressure. And then we can take this constant, we add some sort of roughness constant, and we assume turbulent flow. So our wall stress is dynamic pressure stress, which is the density of water v squared over some sort of roughness. And then we can say roughness and gravity are constant, and the velocity is equal to the square root of the hydraulic radius and the slope of the bed. This equation is called the Chezy equation. And it's derived from the physics that we just went through, where C is known as Chezy's C, the Chezy C. Right? So Chezy said, assuming turbulent flow and the slope of this channel, I can derive the velocity is equal to C which is some constant that's inversely proportional to roughness and the square root of the hydraulic radius and the slope of the channel. Seems to make sense, right? So why don't we use this equation all the time? It makes perfect physical sense. Well, it does make perfect physical sense. And sometime later, someone named Manning came by, Robert Manning, and he was looking at a series of canals in Ireland. And this was in, I believe, the 1880s, sometime in the 1800s. Robert Manning was looking at a bunch of canals in Ireland. And he said, velocity in the canals is better described when the hydraulic radius is raised to the 2/3 power, not the 1/2 power. So then Manning wrote the velocity, and he said the velocity is equal to 1 over the roughness times the hydraulic radius to the 2/3 times the square root of the bed slope. So Robert Manning disagreed a bit with Chezy. Now it's now called Manning's N. This actually used to be called Cutter's N. Because before Robert Manning, Manning's who's very famous for this equation, there is an engineer that actually developed the N value. But today, Cutter gets no credit, and we call it Manning's N. And it represents roughness. But what did Manning get rid of? We had a constant C, Chezy's C, had 2 times gravity over K, the square root of 2 times gravity over K. So we had gravity in it. We had a unit of time in our constant C in Chezy's C. Manning's gets rid of it. He says no. I'm gonna do the 2/3 power into the square root. And remember that square root was a function of that wall shear stress that we solved through dynamics. So Manning said no. And we assume that this roughness N does not change with depth. So N, what are the units of N then? Right? It doesn't make sense. Right? It must have some unit of time in it, but we just call it roughness. We ignore the incoherent units by ignoring that it's now not the square root of the hydraulic radius, which we showed is actually how you would derive this. It's the 2/3. So we completely took the units that made sense from physics and we got rid of it. And we now have Manning's equation. And this is Manning's equation. This is the most commonly used equation in hydraulics to solve for the depth, velocity, or flow in a channel. Now, another thing with units, since we completely destroyed any concept of having correct units by using Manning's equation, if we want to use it in the standard English form, if we want to use it here, what we're going to use in this class is actually 1.49 over N times the hydraulic radius to the 2/3 power times the square root of slope. And these are English. And then if we're in standard units, if you're overseas and you're using this equation, you just use 1. 1 over Manning's N to the 2/3 times the square root of the slope. And these are S standard international units. So this is the most common equation used in open channel hydraulics, is Manning's equation, most commonly seen in English units. So how can we use this? How can we use this equation? Let's go through a quick example. Let's go through a quick example. We're given some sort of channel. Has a bed slope. Inside that channel is some water. The depth of that channel, the depth of that water in that channel is equal to 3 feet. The channel is sloped at 0.015 feet per foot. We assume this depth is perpendicular to the stream bed, that our energy slope is equal to our bed slope. And this channel has some sort of roughness at the bottom of it, and we assume a Manning's roughness of 0.025. Now, do we even know if that's a reasonable roughness or not? We don't know. But we can look into our book, and we can go to page 380. We can see, oh, table 10.1. Here we go. We have some tables for Manning's N. And since Manning's N, since our assumption of uniform flow doesn't change the roughness with depth, we can use these for all of our channel solutions. So we discovered that we have an excavated earth channel with a gravelly bottom with a Manning's N of 0.025. So we got our Manning's N from the table. We went out to the fields. We measured the slope and we got 0.005 feet. We looked at the depth and we measured it at 3 feet. And then we took a cross section of the channel and we noticed it was a rectangular channel that had a base width of 5 feet. And that flow depth, again, was 3 feet. So here's our channel section. So we went out to the field, we measured the depth, we got our roughness from the table for a clean excavated channel. We measured our slope with some equipment, and we measured the width of 5 feet. And we were asked to find the velocity, the flow rate, and the flow regime. Is this channel super, sub, supercritical, subcritical, critical depth? How is this water flowing through this channel? Well, this is pretty simple. Let's use Manning's equation. 1.49 over 0.025 times the hydraulic radius. What's the hydraulic radius? Right? So the hydraulic radius is equal to the area over the wetted perimeter, which equals 3 times 5 divided by what? 2 times 3. One portion, another portion, plus 5. So that's our hydraulic radius. So we have 2 times 3 divided by, oh wait, sorry, messed that one up. We have our area, 3 times 5 divided by 2 times the depth, 2 times 3 plus the base width, 5, all raised to the 2/3 power times the square root 0.015. And we get the quick answer that the velocity is 8.97 feet per second. or 9 feet per second. Okay, how do I know I'm in feet per second? How do I know? Right, because we have the constant for units of 1.49. If we're in English units, we just use 1. All right, so we solve for our velocity. Now, how do we get our flow rate? Well, Q is pretty easy. Q equals V times A, which equals the 9 feet per second, times the 15 square feet of flow area, and our flow rate equals 135. Flow rate equals 134.6 cubic feet per second, or we can just say 135 feet cubed per second. All right, so we found our flow rate too pretty quickly. All right, so how would we find the flow regime? How would we find the flow regime? What would we use? Well, we showed last time that the Froude number, which is a ratio of the channel velocity to the wave velocity, can be used to solve sub or supercritical flow, where D is the hydraulic depth, that is the area of flow divided by the top width of flow. For this scenario, and for all rectangular channels, the top width is equal to the bottom width. Therefore, our hydraulic depth D just equals our depth Y. So our Froude number is solved from our velocity, which is 9 feet per second, divided by the square root of gravity in English units, times the depth of the flow. And that equals 0.91. Now, is that super or subcritical flow? Well, the Froude number is less than 1, therefore it is subcritical flow. It is deeper than critical depth. This sits higher on the energy curve, and the velocity of the channel is slower than the velocity of a wave. But what if someone said, I want this, what is critical depth? I want to know what critical depth in the channel is. How would we find critical depth? How would we find critical depth in this channel? Is critical depth going to have the same flow depth? Right? No, it's not. Because we have to set the Froude number equal to 1, not to 0.91. So we can say 1 is equal to, what happens when we reduce the depth? The critical velocity. Right? 1 is equal to the critical velocity times gravity times the critical depth. So critical depth is smaller, but we hold the flow rate constant. Right? So we hold the flow rate constant, so we can rewrite this equation in Q over A. So now we can solve for Y. Wait, did I do that correctly? I'm going to back up here. Okay, so we can write this as Q over A times the square root of G Y sub C equals 1. Q over A, so now the square root of G Y sub C equals Q over the flow rate. So if we square all of this, we get y critical equals G Q, wait, a Q squared divided by G B squared Y squared. Y critical cubed now equals Q squared over G B squared. So Y sub C, the critical depth of the flow in the channel, can be described by solving for Y sub C, which equals 2.82 feet. So is Y sub C less than or greater than the flow rate in the channel? Right, the flow rate in the channel is greater than Y sub C. We already knew it was subcritical, but now we've solved for both portions. We've solved it two different ways. So the critical depth in the channel is somewhere down here, right? So we're near critical flow. Where does that put us on our energy curve? This is our energy curve, which we can use energy to solve uniform and non-uniform flow. And somewhere straight through that curve, the Froude number equals 1. And that curve, right critical, equals 2.82 feet. Our depth is only 3 feet, or our depth is 3 feet. And we call this normal. Y normal depth is 3.0 feet. So we sit right up here on this energy curve in the subcritical region. Right, so that's a quick example. This is a great test example that I'll be giving. And this is how we use Manning's equation. This is the equation that was originally derived as the Chezy equation with the Chezy C, where that constant actually made sense. It had units of gravity, which is how we got units of time, and it was inversely proportional to some sort of roughness. And then Robert Manning came across, and he said, out of everything I've looked at, it's actually y to the 2/3 makes more sense than the hydraulic radius, the square root of the hydraulic radius, and changed it. Took away the constant, didn't add any gravitational units, and just did this is a Manning's roughness. And so we, in the English units, we have to say 1.49 over n. Because there's really no unit conversion that makes sense, so it's 1.49 over n. And if you're in standard international, it's just 1 over n. So that is how you solve for uniform flow. That's how you solve for the velocity. The velocity is just the flow rate is the velocity times the area. The flow regime is the ratio of that velocity to the depth. And then the critical depth can also be solved for any channel. But are all channels so simply made? Right? Oftentimes we have irregular looking channels. So I'm going to go through an example of how to solve for a trapezoidal channel, which is common. We don't always have these rectangular channels. So how do we solve normal depth in a trapezoidal channel? Question mark. All right, let's assume we have some channel geometry. There's an excavated trapezoidal channel. This is the ground. And in that channel, there is some water. The channel has a flow depth, a uniform flow depth of y, normal depth of y sub n. It has a base width of b, and it has a slope, what we're going to call m. It has a run of m for every 1 foot of rise. And these channels can be different shapes, but we're going to assume m1 equals m2. Now, what is the area of the channel? We've been asked to solve for flow area, wetted perimeter, and top width. Why would we want to know the top width? All right, because our hydraulic depth is what gives us the Froude number. Well, the area of the flow can be split up into triangles. Right. So I'm going to call the top width of these triangles t, small t. And that equals m times y. Right? So for every y, I go over an m. So the total top width is m times y. So the area of flow is equal to 1/2 base times height, which is 1/2 m times y, times y, plus, 1/2 m times y, plus this flow in the middle. That's b times y. So we have some redundancy here, right? We can actually shorten this for the sake of computing something faster, we can call this my plus y. Oh wait, my plus b, my plus b all times y. Right? Y. And then we have two triangles. So we can just, all times the 1/2. So we can just say it's my plus b times y. It's the simplest solution. What is P? What's the wetted perimeter? That's going to be the hypotenuse of the triangle plus B plus the hypotenuse of this triangle. Right? That's going to be our wetted perimeter. So P is going to equal 2, right? There's 2 hypotenuse times the square root of m times y squared plus y squared plus this bottom width, b. So we can shorten this equation to equal 2 times y times the square root of 1 plus m squared. Plus b. So we have an equation for the area. We have an equation for the wetted perimeter. Now let's solve for our top width. All right, well, the top width, t, equals 2t plus b, right? Because this is t, and this is t, and this is b. So t equals 2my plus b, because t equals m times y, where m is the side slope. Okay, So I think we accomplished our geometry session here. We solved for the flow area, the wetted perimeter, and for the top width of flow. What if we're given a quick example? What if B equals 10 feet, the flow depth, Y, is 5 feet deep. The channel is flowing at 5 feet deep. The roughness at the bottom of the channel, we looked up at a table. We got a Manning's N of 0.0. Let's look up at our table. Let's go into the table and say we have a Manning's N of 0.04. 0.040, which represents a sluggish natural channel with some deep pools. We measured that slope of the channel. We gave the slope to equal 0.005 feet per foot. What is the velocity and flow rate in the channel? Is it sub or super critical? Well, I think we can solve this, right? What's our area equal? A equals, and let's define the side slopes is equal to 3 to 1. So we would call these side slopes are 3 to 1. Side slopes are 3 to 1. So A equals 3 times 5 plus 10, all times the flow depth 5, which equals 125 feet squared. And P is going to equal our equation for the wetted perimeter. 2 times the flow depth Y, the square root of 1 plus m squared plus B. And that equals 31.62. Is that all we need to know? What's our equation? What equation are we going to use? Let's use Manning's equation. Where the velocity equals 1.49 over n times the hydraulic radius to the 2/3 power times the square root of the slope. Well, now we know that the velocity equals 1.49 over 0.04 times the hydraulic radius. Wait, what's hydraulic radius? We didn't solve that yet. The hydraulic radius equals 125 divided by 31.62, which equals 3.95. So that's our hydraulic radius to the 2/3 power times the square root of 0.005 feet per foot. And we get a velocity of 6.58 feet per second, right? So we found our velocity using Manning's equation by solving for the hydraulic radius with our area and wetted perimeter. Well, the hydraulic radius is the area divided by the wetted perimeter. So what's flow? Flow equals V times A, which equals 6.58 times our area, 125. So our flow rate, Q, is 822.7 cubic feet per second. And again, how do I know that I'm in cubic feet per second and not cubic meters per second? All right, well, I can see my conversion up here. So you know that 1.49, it's actually 1.486. We round up to 1.49 is for Manning's equation. Well, what's the flow regime? Is this super or sub critical? I don't know. What's our Froude number equal? The Froude number equals the velocity divided by the square root of gravity times the hydraulic depth, where the hydraulic depth equals A over T, which equals 125 square feet divided by what? Divided by T. We haven't solved for T yet. T equals 2 times the side slope 3 times the flow depth 5 plus the flow width, the bottom width, 10. And that equals 40 feet. So our channel up here is 40 feet wide at the top. All right, so D equals 125 over 40 feet, which equals 3.125. Now, is our flow depth, is our hydraulic depth the same as our flow depth? No, it's not. Hydraulic depth is a different term. So our Froude number equals our velocity, 6.58, divided by the square root of 32.2 times 3.125. And that equals a Froude number of 0.655. So our Froude number is less than 1, and that means it is subcritical. Subcritical flow. So this is a great example of a test question. You're asked to find the velocity, the flow, and the flow regime. You might be given a trapezoidal channel, and we said the velocity is 6.58 feet per second, the flow rate's 823 feet per second, cubic feet per second, and the Froude number is less than 1, so it's subcritical flow. All right, well, that's our lecture for today. Thank you for watching this. I know if I'm going too slow, at least you can zoom forward and save yourself some time. And you can also check out those whiteboards. I saved those whiteboards, so I'm going to upload those to Canvas. I'm going to be posting some homework. It'll be another quick quiz, and it's going to go over some of the things we didn't cover in runoff, like runoff volume. You're going to be asked to solve the rational method, estimate the volume under a hydrograph. And then I'm going to make some homework for these open channel questions so we can get used to solving these open channel assumptions using Manning's equation. Even though we know that the units don't always work out, that's the equation that we use. It's a very common equation. And then we're going to begin to get ready for our exam. So we got an exam coming up in 2 weeks. So let's do some review. Let's make sure you're able to go through the homework and these questions and watch these lectures. And please bring any questions to me on Wednesday. Thank you very much, and I look forward to seeing everyone on Wednesday.